Okay, so this video is for any of my students who were not present during the review for the quiz over sections 4.3 and 4.4 of pre-algebra. So hopefully you have the quiz review in front of you. So let me go ahead and dig into the assignments, and my pen has decided to not work. Hold on just a second. Let's see here. Quiz. 4.3 and 4.4. So this is the greatest common factor and least common multiple. This should all be review. You've had this in your arithmetic classes, but we're also going to just do a little bit more review about determining this for variables, which applies a little bit more to the pre-algebra that we are going to be doing more of in this chapter. So section 1 covers greatest common factor. Now, remember, when you are looking at a multiplication problem, remember that the factor times the factor equals your product. This is, these are the different terms in a multiplication table. So the factors are the smaller numbers in the multiplication product, and the product, you can think of that as the multiple. That is the larger number, right? I mean, that makes sense logically. So when you're looking for greatest common factor, you're looking for these guys, the smaller number. What is the greatest, the largest small number that evenly divides into a multiple or a product. And so that's your greatest common factor. It's always going to be one of the smaller numbers. When you're looking at least common multiple, you're looking at the product of two numbers. So you're looking at what is the smallest number that both of these numbers I'm comparing multiplied by another integer will produce this least common multiple, this product. So just to kind of make sure you know what you're looking for and remember what you're looking for with greatest common factor versus least common multiple. Because I know it's very confusing, especially when we're studying both at the same time. So the first half of your review is involved with the greatest common factor. So those are going to be the smallest or the smaller numbers that factor into the numbers that you're looking at. Okay, let's put all these words into practice. Let's look at the math. Okay, so for number 1, we're comparing 8 and we're comparing 18. So let's go and do our prime factorization here. So 8 breaks down into 2 times 4, and then 4 is not a prime number, so we keep going, and we end up with 8 has a prime factorization of 2 cubed. And then 18, we have 2 times 9 equals 18. So then 9 is not a prime number, so that breaks down to a 3 and a 3. So 18 prime factorization is 2 times 3 squared. Now, when you look at this, you must find what is the greatest number, combination of prime numbers that that are part of the prime factorization of both 8 and 18. And in this case, we see that there is a 2 in both. We also can see that there's not a 3, so we can just eliminate the 3 squared because that doesn't exist in the prime factorization of 8, so it cannot be included in the greatest common factor. Also in this case, the 2 in 18 is common in both, so you cannot use 2 to any other exponent because otherwise it's too big and it won't fit into 18. So our greatest common factor here is 2. That's as big as it gets. All right. So let's look at number 2. So number 2 gives us 15 and 36. All right, so 15 breaks down into 3 and 5, both of which are prime numbers. So that's our prime factorization. 15 is 3 times 5. 36 is going to be a bit bigger. 2 and then 18. And then we just did that up top. So that breaks down into 2 and 9, which breaks down into 3 and 3. So the prime factorization for 36 is 2 squared times 3 squared. All right, so we can look in the 15 and we see a 5, but we check 36, there's no 5. So that's not going to be included in our greatest common factor. Same thing with the 2. There is no 2 in the prime factorization of 15, so it cannot be included in our greatest common factor. So we have a 3 and we have a 3 squared. Now, you must choose the one with the lowest exponent because 3 exists inside 3 squared, but 3 squared does not exist inside 3, right? It's too big. It's too many 3s. So our greatest common factor is 3 between these two. All right. Moving on, number 3 is a little more complicated. We have 12, we have 36, and we have 45. All right, so again, in this one, I'm going to guess that 3 is probably the greatest common factor between these, but let's actually work through the prime factorization and find that out. So 12 breaks down into 2 and 6, which that breaks down into 2 and 3. So the prime factor, or the prime factorization for 12 is 2 squared times 3. 36 is 2 and 18. We just did this in number 2. This breaks down into 2 and 9, 3 and 3. So 36's prime factorization is 2 squared, 3 squared. All right, so let's look at 45. I don't think we're going to see a 2 in 45. All right, so I would break that down into 5 and 9, and then 9 breaks down into 3 and 3. So 45 has 3 squared times 5. Now remember, and if this is easier for your brain, do it. Break those exponents up if you need to, especially when you're only working with, like you're actually doing your prime factorization, you're working with smaller numbers. You can do that. So this you could do 2 times 2 times 3. Meriwether. I don't know why my cat loves to walk on my screen when I'm doing this. 2 times 2 times 3 times 3, and then 3 times 3 times 5. All right, so I don't know about you guys, but I already know I only see 1 5, so that's not going to be included in my greatest common factor, because when you have a greatest common factor, it must exist the same number of times in every single number that you're comparing. Also, in number 45, we have no 2's. So you can just eliminate all of your 2's because they don't exist here. Now we have 2 3's left in 45, and we have 2 3's left in 36, but we only have 1 left in 12. So that means that only 1 3 is in our greatest common factor. Let me show you with this one too. Once you have determined which ones are common in every single number you're comparing, then just pick one of those numbers and just look at that one. I don't want you to make the mistake of thinking that you have 3 3's in your greatest common factor. You have 1 3 that exists in the prime factorization of all of these numbers. So just look at one, add them all up. If you have more than one number, and you find in this case, the greatest common factor is 3. That's our answer. Okay, so number 4, number 5 get into problems where we're looking at the final factorization of some sort of number. Usually when we have these problems, the original number is humongous. So they're just going ahead and giving us the prime factorization, and then we need to pull out the greatest common factor. So let's look at number 4. And we see that we have 2 cubed times 3 squared times 5. And then we have 2 squared times 3 squared times 5 squared. Okay. All right. So this one is a nice example because we have, you look at your base number. If that base number exists in both numbers you're comparing, then at least one of them is going to be included. In this case, all three exist in both numbers, right? We have a 2 to an exponent, a 3 to some sort of exponent, and a 5 to some sort of exponent. So once you've determined that, you just look at the ones with matching base pairs and find the one with the smallest exponent, and that's the one that gets included in your greatest common factor. So for example, if I had, and we'll see this in the next one, if I had a 7 here, because I don't have a 7 as a base prime in both of these prime factorizations, that would not be included in my greatest common factor. It must exist in both. But we'll look at that more in depth later. Okay, so first off, let's look at our 2's. So in the case of a base number 2, we have a 2 cubed and we have a 2 squared. Now, which one is the smaller number? It's going to be the one with the smaller exponent. So in this case, 2 squared is what's going to go in our greatest common factor. And if you want, you can mark through the 2 cubed because it's not going to work. All right, 3 squared is in both. So therefore, 3 squared is part of your greatest common factor. So you can go ahead and put that over there too. Now look at 5. Now a 5 by itself, remember that's an understood exponent of 1. So the 5 alone is the smallest exponent. So we would just multiply that times 5. So once you do that, then go ahead and solve it for a number. So our greatest common factor is 4 times 9 times 5. 4 times 9 is 36. And 36 times 5, let's see, 5 times 30 is 150. 5 times 6 is 30. So your greatest common factor is 180. Okay, so let's do another one of these, number 5. So number 5 gives us 3 times 5 squared times 17. And the second one is 2 squared times 3 squared times 13. Okay, well, we can very quickly see with these odd numbers here, 17 and 13, those are not common. They don't exist in both of these numbers. So those are instantly not part of our greatest common factor. Also, we see that we have a 5 squared in our first number, but there's no 5 base number in the second. So we mark through that. Same thing with our 2. There's a base of 2 in the second number, but not in the first. So that's not included. So now you have 3 and you have 3 squared. Which one is the smallest? 3, right? Because that's an exponent of 1. That one's a little bit easier, but you see how you just instantly eliminate any any base prime number, no matter what its exponent is, that only exists in one of the numbers or does not exist in all of them if you have more than 2. So in this case, our answer is 3. Okay. Let's look at 6 and 7. So now we throw variables into the mix, which I feel like once you understand, the variables are the easiest part of this entire thing because you're really just looking at the exponents once you've determined if the variable is common in all the numbers. So let's look at number 6. So number 6 is 9c cubed d to the 5th and 12 c to the 4th, d to the 7th. Right, so for the first part, I just go ahead and look at your coefficient, which is your constant that goes in your that's part of your term, and go ahead and do the prime factorization for those coefficients. And then find the numerical part of your greatest common factor, and then go back and look at your variables. Okay, so 9 breaks down into 3 and 3. Those are both prime numbers, so we're done there. 12 breaks down into 3 and 4, which is not prime, so it comes down to 2 and 2. Okay, so when you look here, you can see that your greatest common factor between these two is the 3. So 3 is going to be part of our greatest common factor. And now look at your variables. So you want the same letter to exist in both numbers if you're going to include it in your greatest common factor. In this case, you can see that we have c cubed and we have c to the fourth. So we have c in both. So we're going to have some sort of c. And then we have d also in both, d to the power 5 and d to the power 7. So you're going to have a c and you're going to have a d. Now, of your variable c's, I guess I said that right. Which one has the lowest exponent? Well, we see that it's c to the third. So that's going to be the one included in our greatest common factor. Same thing with your d. When you look at your d's, you see that d to the fifth has a smaller exponent than d to the seventh. So d to the fifth is part of your greatest common factor. So that's your final answer, 3c cubed d to the power 5. Okay, so let's look at number 7, which has 3 different terms that we're looking at. Number 7 has 16m to the power of 18, n to the power of 4. We have 64m to the power of 15, p to the power of 6. And then our last number here is we have 36m to the power of 10, n to the power of 7. Okay. So I would guess probably 8. I know 8 divides evenly into all of these numbers. So 8 is probably our greatest common factor, but let's look at our prime factorization and see. So in this case, we have 2 and 8. 8 breaks down into 2 and 4. 4 breaks down into 2 and 2. So 16 has a prime factorization 1, 2, 3, 4 of 2 to the fourth. All right, 64. Oh my gosh, I think this is like so many 2's. 2 times 32. 32 breaks down into 2 and I've lost it. 16. 16 breaks down, well, we just did that, into 2 and 8, and then 2 and 4, and then 2 and 2. All right, so we have 1, 2, 3, 4, 5, 6, 2. So 64 is 2 to the power of 6. 1, 2, 3, 4, 5, 6. Yep. All right, and then 36, 2 times 18. 18 is 2 times 9, which is not a 2. 3 times 3. All right, so 36 is, so maybe not. Oh, that's right. 8 doesn't go 36. 4 does. I was thinking that was 32. All right, anyway, so we have 2 squared times 3 squared. All right, so when we go and look at this, we see that the 3 in 36 does not exist in the other two numbers. So we have a base number of 2, one with an exponent of 4, one with an exponent of 6, and then 1 squared. Which one is our smallest? Obviously, it's this guy right here. So when you're calculating your greatest common factor, you know that your coefficient in this case is going to be 2 squared, which is 4. Okay, so let's go back and look at our variables. So we have an m in all 3 of these. So we'll come back to that in a second. So we know we're going to include m to some power. Put that down there. All right, and then we have an n in the first one. There's no n in the second one, so instantly you can cancel out any n's because they're not going to be in your greatest common factor because they don't exist in 64m to the 15th, p to the 6th. Now you can look at that second number and you see that it has a p to the 6th, and there is no p variable in any of the other numbers. So you would mark through that one. It's not going to work. So m is our only variable that can be part of our greatest common factor. All right, so m, which one has the smallest variable, or excuse me, the smallest exponent of 18, 15, and 10? What's that last one? So it's m to the 10th power. All right, so your greatest common factor is 4m to the 10th. All right, number 8. Excuse me. Okay, so for number 8 through 15, we work with lowest common multiple. So remember your, let's say lowest, least, whatever. Your least common multiple is going to be a large number. It's going to be larger than the numbers that you're comparing. because both numbers you're looking at must be able to be multiplied by another factor to equal this multiple or this product. So remember that when you're looking at LCM, or least common multiple. So number 8, we're kind of using the same format here. So we're looking at 7 and we're looking at 9. All right, well, 7 is a prime number. So 7 is its prime factorization, but 9 breaks down into 3 times 3. So, excuse me, when you are calculating least common multiple, you actually multiply all of the base numbers at the highest exponent there they are shown in the prime factorization. Let me show you what I mean, because that's kind of hard for me to say. So in this case, we have a base number of 7. So if you're looking at lowest common multiple, you're taking every base number and making sure it's included in calculating that multiple, that least common multiple. So we have 7 and we have 3 squared. So in this case, both of those must be multiplied together to give you your lowest common multiple, which means that 7 times 9, which gives us 63. 63 is the lowest common multiple. I keep saying this, I'm gonna keep saying that. Okay, so 7 times 9 equals 63. So that is our LCM here. Let's look at another example. Number 9 is 15 and 35. Okay, so what we're doing is we're finding what number does both 15 and 35, you could say divide evenly into, or when multiplied by integers equals this number. So again, we just break down the prime factorization. So 15 breaks down into 3, that was messy, 3 and 5. 35, I would start with 5 times 7. Okay, so 15 equals 3 times 5, 35 equals 5 times 7. So we have a 3, we have a 5, we have 5 in both, and then we have a 7. That 5 is already included in the other one. So when you're finding your least common multiple, it is 3 times 5 times 7, which is 15 times 7, which equals 105. That's your least common multiple, 105. All right, hopefully that's pretty easy. Like I've said, we've seen all this before, but it's been in other classes a long time ago. So we're just reviewing at this point. All right, last one is 8 and 14. So 8 breaks down into 2 times 4, which breaks down 2 and 2. 14 is 2 and 7. Okay, so this is what I'm talking about when you make sure you choose the base number with the highest exponent. So it's the opposite of what you do when you find your greatest common factor. All right, so 8 is 2 cubed, whereas 14 is 2 times 7. Well, there's a base number of 2 in both here, but you want to use the one with the highest exponent. So in this case, we're going to use 2 cubed. And then, of course, we also need to use 7 when we calculate our least common multiple. So to calculate this, it's 2 cubed times 7, which is 8 times 7, which is 56. Right, 48, yep. I don't know why I always have to think a little harder when I'm multiplying like my 8s and 7s and 6s. All right, so 56 is our least common multiple between 8 and 14. All right, so number 11. So number 11 and number 12, they were already given the prime factorization of 2 large numbers. And so we need to determine what the least common multiple between those 2 is. These are going to be some pretty big numbers. So 3 times 5 squared times 7 is our first number. And then 2 squared times 3 times 5 times 11. Okay. So I usually just look for my smallest number. There's a base number of 2 here, but there's only one. So I don't need to compare my 2's in each individual number and see which one has the highest exponent because I only have one. So when determining my least common multiple, I'm going to have 2 squared. And I've included that, so I'm marking through it. All right, there is a 3 in both, but it's just 3. It's 3 to the 1 power. So you just include 3. As long as you include 3 in your greatest common multiple, that's enough to cover the 3 in both prime factorizations. Okay, now we also have 5, but in one we have 5 to the power of 1, and one we have 5 to the power of 2. So we want to use 5 to the power of 2, the one with the larger exponent. So we've used both of those. Moving on. And then we have a 7 and we have an 11. So we have to include both of those. Okay. So let's break this down. 2 squared is 4. 4 times 3 is 12. 5 squared is 25. And then we have 7 and 11. All right, so 12 times 25. 25 goes into 100 4 times. So that's 300 times 7 times 11. And then 3 times 7 is 21. So that's 2100 times 11. And that I'm going to let my calculator do. It is too late in the day for this. Let's see. So clear 2100 times 11 gives me 23,100. That is the lowest common multiple that both of these crazy numbers go into. So that's what I'm telling you. They start to get big. That's why if you guys can at least determine the correct prime factors to use in calculating it, I am totally okay with using a calculator to add them all up. Because if you messed up the most important part, you're not going to get the right answer, whether you have a calculator or not. All right, so 23,100. Okay, so let's look at number 12. Number 12 compares 2 cubed times 3 times 5 cubed times 7 cubed to 2 times 3 squared times 5 cubed. All right. So as you can see from this one, we have 3 base numbers that exist in both prime factorizations. So just compare them, find the one with the largest exponent, and that's the one you're including. So we're going to include 2 to the third. So we're not using this guy. If we look at our 3, and these are multiplication, I kind of make them look like variables. All right, the largest with the base number 3 is 3 squared. So that's going to be part of our least common multiple. 5, we have 5 squared and 5 cubed. 5 cubed is our bigger one, so that's the one we're going to use. And then we've got to use this 7 squared as well. So our least common multiple is 2 cubed times 3 squared times 5 cubed times 7 squared. All right, so that's 8 times 9 times 125 times 49. Hello, calculator. 8 times 9 times 125 times 49 equals 441,000. Humongous, but that is correct. Okay, 13, 14, 15. Honestly, especially when it comes to least common multiple, I think that working with variables is by far the easiest, but you've got to remember the process in order to be able to say, oh yeah, this is easy, I got it. So don't worry if you're still struggling. It just takes a while for it to click sometimes, and that's okay. All right, so for number 13, we have 4. I don't know why I did this to myself, G and J. I can look at a G and say J, so I confuse myself really bad, and I know I confuse you guys, so I'm sorry in advance. Okay, 4G to the third, J to the fifth is the first number, and then 6H cubed J to the fourth. Okay, so just like we did with greatest common factor, I want to go ahead and break down my coefficient to its prime factorization. So we have 2 and 2, and we have 2 and 3. So remember, when you're looking at least common multiple, you got to include all of them. So we have 2 squared over 6. We have 2 times 3. Well, we have 2. We have a 2 in both prime factorizations, but use your larger one. So 2 with the higher exponent, and then 3. So with your least common multiple, you're going to have 2 squared times 3, which is 12. Excuse me. All right, so now let's look at our variables. All right, so again, with least common multiple, you have to include all the variables. So you're going to have a G, a J, and an H. So G, H, J. I always put them in alphabetical order. And that's, I guess you would call it algebraic etiquette. Sure, keeping things in the right order. All right, so G, we have a G cubed, and that's our only G, so G cubed goes in there. It looks like we have J in both, so you find which J has the larger exponent. Well, that's J to the 5th, so that's the guy we're going to include here, J to the 5th. And then you have H cubed. It only exists in one, so you don't have to compare and pick the larger of the two. Just bring that one down into your least common multiple. And then that gives your answer. It's 12 G cubed H cubed J to the 5th. Done. Okay. Number 14. So for number 14, no coefficients. Yay. So let's go ahead and just compare our terms here. We have m to the 18th n squared, and we have m to the 15th p to the 6th. All right, so we do have m in both, so use the one with the larger exponent. So m to the 18th is going in our least common multiple. M, n, and p, those are our 3 variables. Throw them on down there. You're going to be using all of them when it's the least common multiple. You just have to go back and make sure you pick the one with the largest exponent. So in this case, m is the only one that we're comparing. So m to the 18th. The others, you just bring them on down. So n squared, p to the 6th. That's it. M 18, n to p 6. All right, last one. Let's look at number 15. So for number 15, we have 10. Let's see what I did here. R cubed s squared t. R squared t. And then we have 25. I don't know why I do that with my 5s. 25r squared s cubed. All right, so break down these coefficients. 10 is 2 and 5. 25 is 5 and 5. So when you lay that all out, you end up with 2 times 5 for the 10. 25 is 5 cubed. So we've got to include the 2 and then compare the 5s. The 5 squared is the larger of the 2. So when it comes to the coefficient of our least common multiple, it is 2 times 5 squared. All right, so now let's go back up and look at our variables. We have an r in both. Which one has the larger exponent? It's the r cubed. So r cubed. S, we also have s in both, but s cubed is over here with the 25r squared s cubed. So that's the one we use, the bigger one, s cubed. And then we have a t, so he comes down and joins the rest of the party. All right, so go ahead and simplify by solving your coefficient, and you find out that your least common multiple is 2 times 5 squared, which is 2 times 25, so 50 r cubed s cubed t. Okay, and that's it. R cubed s cubed t. So follow this along. Make sure you fill out neatly on your review sheets. Those can be used along with your notes for the quiz. And put an asterisk, a star, or a question mark by any of these that you want to go over one-on-one with me before you take the quiz, if that's possible. So otherwise, good luck, and I will see you guys in class. Thank you. Bye-bye.